Let us continue the discussion on overview of experimental stress analysis, and we have discussed in the last class the problems considered are beam under 4-point bending. Now we come back to the stress field analytical approach. Now you have got the stress field, you have also seen the stress tensor. With your knowledge of mechanics of solids, it is possible for you to find out the strain tensor. It is not difficult at all. Can I request you to look at, brush your old memories and find out how do you find out the strain tensor, because you have the stress tensor is available. From stress tensor you can easily find out the strain tensor, and you have to be very careful while applying this step. And what you find here is stress tensor, you have only one component, it is a uniaxial state of stress. The moment I go to strain tensor, I find something different. I find strain tensor is no longer uniaxial, but it is triaxial. And can you say what is the value of epsilon xx, epsilon yy and epsilon zz? And epsilon xx, there is no problem. You would be able to directly write from your understanding of even simple tension test. And what many people may ignore is the effect of Poisson's ratio. They may ignore the presence of epsilon yy and epsilon zz. You have to be very careful about that. There is a possibility that you may ignore the presence of these two strain components. So what you have is, you have a stress tensor which gives you uniaxial state of stress. On the other hand, when I go to strain tensor, I have a triaxial state of strain. You may ask, suppose I make a mistake and I go and interpret the experiments, will the experiments understand this or not? I have always been saying experiment is truth. You may make approximations in your formulation to simplify your mathematics, and in some cases if the values are reasonably small we may also ignore it, but the moment you come to experiments they always reveal the truth. And what is the role of this strain components epsilon yy and epsilon zz? You have a Poisson ratio here, and you have when you have the beam under bending, I would like to show you the model. If I take the model and bend it, and what I have here is the beam bends here, and this is one curvature you have, and this is what you do it in your simple strength of materials approach. I have said that in addition to this you also have strain because of Poisson effect, and what you find is if you look at sideways, what I find is I have a bulge at the bottom and it is not bulging out in the top. Why this has happened is, in the way I have bent, this fiber is subjected to tension and the inner fiber is subjected to compression, and what happens because of the Poisson effect, the bottom portion bulges out and top portion narrows down. And you also see one more interesting thing, you have additional curvature here because of this, and this curvature is known as anticlastic curvature, and none of this you might have heard in your first level in strength of materials if people have not gone deeper into the analysis of beams. Only when you go deeper into the analysis of beams you will find that these concepts you have to look at it. And what happens, the experiment looks at it, experiment reveals this, and that we will see very closely when you see the fringe pattern. We will see the fringe pattern, it will take a second for it to come, and what you will see is when I magnify it, you will see in a very subtle fashion what you have on the top fiber. In this particular example, the top fiber is subjected to compression and bottom fiber is subjected to tension. So you will have the fringe order slightly greater than what is there at the bottom. So it is not perfect symmetry. So the experiment captures this, You may call it as anticlastic curvature, but experiment reveals this information. So you will not have perfect symmetry, there will be small deviation, and you should not come back and say I have done the experiment is wrong. It is not so. In your analytical evaluation of stresses, if you also bring in the effect of Poisson ratio effect, then the stress patterns will be like this. So experiment always gives you truth, and that you should never forget it. Okay. Now what we are going to do is, we will again go back to the slide, and what we will do is, we have seen the stress tensor, we have seen the strain tensor. Now with that information, using mechanics of solids, that is using the equations of theory of elasticity, you could integrate the strain quantities and get you the displacement values. And I do not think you would have done it in a first level course, because you are happy with the stresses, you are happy that in bending central core does not contribute to load sharing. That is all, you focus on that, and you do some exercise on finding out beam deflection. Beyond that, you do not go and study it deeper. Now when I look at this, I can get the displacement field, and displacement field is like this. It is fairly simple. I have this u equal to m by ei into xy, and this is nothing but an equation of an hyperbola. So when you plot the contours, you will have the contours looking like hyperbola, and you also have an expression for the v displacement, which is given as m by 2 ei into x squared plus nu times y squared. And in your deflection calculation, you may not have calculated u displacement at all, you would have only found out the v displacement, you would not have found out the u displacement, you would have determined only the v displacement. Now what we will do is, we have seen the fringe pattern from photoelasticity, which gives the essentially contours of sigma 1 minus sigma 2. Now our interest is to see other contours. What I can do is, I can do a contour on, I can look at geometric Moire and find out how the displacement field is, and this is what the u displacement, and this is what the v displacement, and we would see this little closely, and what we will see is what you see here. I have the fringes labeled, and you have a 0.5, 1.5, 2.5 like this, and you have minus 0.5, minus 2.5. So once I go to displacement, I have both positive and negative numbering of the fringes. This is first observation. The second observation is, the fringe pattern comes with an indication on what is the grating direction that has been used. When you go to Moire, for me to reveal the displacement information, I have to use a grating, and grating direction dictates what component of displacement I do get. And I would like you to have a reasonable sketch of this, and when you do this, you will have an idea how the whole field pattern looks like. And there are many indirect learning you learn. One is, suppose I change load, and you see this is how the fringes are developed. As the load is increased, more and more fringes are developed, and this is a very key information in most of the experimental techniques to label the fringe orders as an auxiliary method to do that. Another one, what you find is the fringe thickness is different. This also carries some information, this we will see later part of the course. So you have a familiarity when I want to look at a displacement field in the case of a beam under 4-point bending, it would look like this. And we will also have a look at the v displacement. Have you been able to make a reasonable sketch of this? Okay. So what I will do is, I will see the v displacement, and v displacement is like this, and here you find I have the grating direction horizontal. So by comparing these two figures, you can easily understand what I say as displacement is a component perpendicular to the grating direction. And what I want you to note down is, when I have a grating direction in one way, I need to have one optical arrangement to record it. When I have the grating direction in another way, I need another optical arrangement to do it. And this is what I have said earlier, experiments will reveal information of a particular kind. They may have the capacity to reveal more than one information, but they may require two different measurement scenario. And when I have two different measurement scenario, what I need to do is, I need to have, there are also methods where they combine and try to get more than one information in one go. When we look at Moire, we will find out how you can get both u and v displacement simultaneously. And what you should keep in mind is, if I get two information together, it is always a nuisance. And here again we can see, as a function of load increase, how the contours appear. And this is very important, and this will give you a sort of understanding. It also gives you a feeling of doing the experiment right in the class. When I increase the load, I see fringes are formed, and here again the labeling, I have positive and negative quantities. If you have noticed very carefully, in photoelasticity we have not labeled negative fringe orders, we have labeled all of them as positive, and this is an important point that you have to note with. Suppose I want to find out the strain, what do I do? Now I have the displacement, I differentiate the displacement, it is possible for me to find out the strain, but I may not want to do that if I have my record from geometric Moire, because geometric Moire gives with less accuracy, and I have to go to Moire interferometry and then do the differentiation and get the strain field. Strain at discrete points could also be evaluated by strain gauges. Suppose I want for a series of points, then I have what is known as a strip gauge. In one backing, several strain gauges are available at fixed lengths given by the manufacturer. This is done by, at the time of manufacture itself, one grid containing several elements of strain gauge. So I can get the strain from strain gauges from point to point or along a line of interest. So we have seen reasonably various contours that is possible from experiment for the problem of beam under 4-point bending. Now let us move on to cantilever beam. And what is the difference? Because of the load here, you have bending moment varying across the length of the beam. That is what is seen in the first term here. You do not have a bending moment, but the bending moment is a function of x, that is what you find here. And in addition, you also have a shear stress, and for convenience the stress tensor is simply given as stress field, where I give only the component sigma x, sigma y and tau xy. A fairly straightforward, this you have a solution from strength of materials. What you may not have done is, you may not have calculated the strains, and the strain field looks like this. I have minus p xy divided by Ei, epsilon y is nu times p xy divided by Ei, and gamma xy is minus p times c squared minus y squared divided by 2 Ig. And obviously here the stress field is little more complex, strain field is little more complex, and you will also anticipate the displacement is going to be complex than what you have seen in the case of a beam, and we will have a look at it. And the point to note here is, when I do an analytical method, I am able to get the stress field, I am able to get the strain field, I am also able to get the displacement field, and that is what you see here. And displacement field is slightly more involved, and you would have worried in your basic course in strength of materials only on the V displacement, and when x is 0 you get PLQ by 3 Ei, and you do not find out what happens for the V displacement as a function of y. And what you need to keep in mind is, you have simply taken a 2-dimensional beam as simply a line and then analyzed it. You are not considered this as a beam and then analyzed it. When you consider it as a beam, you will also have to have a variation over the depth y, and that is why you have the u expression. If you look at it, is minus p x squared y divided by ui divided by 2 ei minus nu times p y cube divided by 6 ei plus p y cube divided by 6 ig plus within brackets p l squared by 2 ei minus p c squared by 2 ig multiplied by y. And what is the interesting thing about this expression? When y is 0, u is 0. So, you do not find out u displacement at all in strength of materials, mainly because you are considering a 2-dimensional problem as a 1-dimensional problem. So, when you come to theory of elasticity, you have made an improvement, and obviously now we will go and look at what the experimental methods give as contours. So, first thing what we have always been doing is photoelasticity, and you all know that it gives you contours of sigma 1 minus sigma 2, and these contours you would not be able to calculate right at the class. You need it is better that you have a computer software to evaluate it, and also have a post processing where you can go and plot it. As before, I would like you to have a reasonable sketch of these fringe patterns, and what you find here is these fringe patterns are definitely different from what you have seen in a beam under 4-point bending. So, what you find is the stress field is different, which your contours directly bring out. You have the effect of shear which is embedded in this stress field. And another important point to note is on the center of the beam you have a light shade of blue, it is not black like what you have in your 4-point bending, and this is the load application point where you have fringes concentrated, and this is how this is the clamped end, and this is how you get experimental isochromatics. So, experimental isochromatics are different from what you have seen in the case of beam under 4-point bending, and naturally the displacement contours is going to be still more complicated. So, you have u displacement, you have v displacement, and what you have here is I again have a grating direction, and knowing this grating direction it is possible for you to say it is u displacement. Knowing this grating direction it is possible for you to say this is v displacement, and you also have a feel of doing the experiment by seeing what happens as a function of load. I gradually increase the load and more fringes get formed, and you could make a simple sketch of it. Try to get only the skeleton, you do not have to draw the band, you get a geometric shape and a few fringes which will give you an idea how do I get the fringes in the case of a cantilever beam subjected to a end load, and I can increase the load, more and more fringes get formed. Then I can also look at the v displacement, this also I can look at as a function of applying load, and you will see as the load is increased you notice this zone more and more fringes develop and they become denser in appearance. I increase the load 2, I increase the load 3, increase to 4, 5, 6 and 7. So, what you find here is it become almost like parallel lines, more fringes are seen in this zone, and when you draw the sketch it is not necessary that you draw all these lines, you just draw a few lines indicative that you have fringes like this, and it slightly changes curvature as it goes close to the clamped end. And these are simulated fringe contours. As I have said, some of you who have an exposure to computer graphics can make an attempt, you have those equations, you could go and make a contour plot and bring it to me, and you will have a doubt how to get the fringe width. Let me keep that as a secret for the moment, and we will see how to get this band also when you do the plotting. In this class, we have looked at the strain fields of 4-point bending and the effects of Poisson's ratio, which is subtle but quite important for data interpretation. Then we have looked at how the shear stress influences the color of the central axis in a cantilever beam. We have also looked at the displacement fields for a cantilever beam and the corresponding fringe patterns from Moire.